Good morning, class. How you doing, physics? It's a rainy, dreary Monday, but we're gonna make it sunny and bright and happy because we're gonna be doing physics. What better way to spend a dreary, rainy Monday morning than unlocking the secrets of the universe? Hi, Holly. Yeah, rainy days. Some rainy days here and there. Very good thing. Very good thing. All right, gang. So you have an exam a week from today. All right, and the format is going to be exactly the same as last time. It'll be administered on Sakai, and you'll be expected to take photos or scan your work and submit that along with your answers for the multiple choice questions with the assignment. Okay, so that's a week from today. It's supposed to be on Friday. It's listed as Friday on the syllabus, but moved it to Monday. So this week we really need to refine your skills so that you are going to succeed and you are going to ace this test. All right. The material on the test is Newton's laws of motion and work and energy. So there's a lot of material on this test, on this exam, a lot of ground covered, but you have a week and just commit to it now. Don't say to yourself, I want to do well on this test. Don't say that. You got to decide that you're going to do well. There's a big difference between wanting to do something and deciding that you're going to do something. Decide that you're going to do well, and then prepare yourself. All right. So, got any questions while we're talking today? Put them in the comments. Let's start by taking a look at Sakai and the summary of week. We're in week 8 now. Week 8 of week 8's lessons. All right. So we, in the lessons tab here, I've been summarizing what we've been doing as we go along. So, what you should be doing this week is finish reading these chapters that deal with work and energy, and Chapter 7 deals with work and kinetic energy, and Chapter 8 deals with potential energy and conservation of energy. Okay. I put together a video tutorial on 2 kinds of potential energy, and it should be, let's see if this link works. Yep, link works. So it's one of your homework problems. As I told you guys on Friday, it's the problem involving the springs. The spring launcher. Links to slide decks that might be helpful, including slides for conceptual understanding. There's a typo there. It's not Newton's laws. The link here is to work and energy. I bet that same typos in week 7. I'll fix it in a second. Then finish the homework assignments. There's 2. One is due tonight, work and kinetic energy. And the other one is due on Thursday, potential energy. All right, so make sure you finish this one before 11:59 tonight. And this one's due on Thursday. And then you can watch video replays of lessons on YouTube. All right, so this is going to bug me. I'm going to have to go fix that typo. Yeah, same typos here. Not Newton's laws, work and energy. Okay. So I do want to talk about, there's a concept. Let's go to the homework here. There's a concept in the homework which is this concept of power, and there's 2 questions that deal with the concept of power on the problem set that's due tonight. And so let's talk about this a little bit and talk about what power is. And so one of these questions deals with electric energy and power consumption of electrical appliances. So we'll take a look at that. But it's once you understand what power is and how it's related to energy, most of the extra stuff that deals with electric power is just unit conversions, converting from one unit of energy into another. And so we'll take a look at that. All right. All right, so power. What is it? Power in physics, power is defined, let's call it P for power. Power is defined as a ratio, and the numerator is a quantity dealing with energy or work. So I'll write it as work or energy, and the denominator is a measure of time. And so unit-wise, work and energy both have the same SI units, the joule. So unit-wise, it's a joule, and the SI unit for time is a second. So power, the standard units of power in physics are joules per second, and that is also a watt. Okay, or W. So, oh, great, now we have another W. We have W for weight, W for work, and now W for a unit called watt. All right, context is everything. Don't get confused. Here the W is a unit for power called a watt. So what exactly is this? Well, work and energy, think of power as a measure of how much work is being done per unit time. And what is work? Well, it's energy, changing forms or moving from one place to another. So oftentimes power is a measure of energy conversion per unit time. That makes it a rate. It's a rate. Power is a rate. And if you tuned in on Friday or came to recitation on Friday in person, I showed you a video of the triple track. And one of those three situations, the tracks were different. They had different inclines on the roll up, and but they were all the same when it came to conservation of energy. The ball starts with potential energy, gains kinetic, and ends with potential energy. So they were all the same in terms of, in absolute terms, energy at these three critical points in the motion of the ball, rolling down, rolling up. They were not the same when it comes to the rate of energy conversion on the uphill incline. So I said it takes longer for this ball on this gentle incline to come to rest. And the embedded in there is the concept of time. You have energy conversion that's taking a longer amount of time. That's less power. Less power. Energy per unit time. So same amount of energy, but a greater amount of time, that means smaller power. Okay, so power helps us quantify the rate of energy conversion. So let's see, the situation here dealing with an air conditioner. Hi Kaylee, I'm just seeing your happy good morning right now. Good morning to you, Kaylee. Air conditioner, and in my problem, the air conditioner has a power rating of 10 kilowatts. Okay, so there's an air conditioner, and its power rating is 10 kW. Well, what's a kilowatt? Kilo is 1,000, so that's 10,000 watts. Okay, what does that mean? That means this air conditioner is in the business of converting 10,000 joules of energy every second. All right, what is that energy? What does that convert? Well, think about how electrical appliances work on electricity. So the energy that's being converted is electrical energy to some other kind of energy. So what does an air conditioner do? It has compressors in it, and so some of that energy is converted to heat, some of that energy is converted to mechanical motion, um, and but ultimately all of that energy is coming from the wires, the electrical wires that are running to your house, and it starts as electrical energy. What kind of energy is electric energy? Well, microscopically, it's potential energy. Microscopically, we'll learn this. You'll learn this next semester. Is that you have electrons that are motivated by electric forces, and the amount of energy an electron has due to electric fields, which are mathematically very similar to gravitational fields, can be modeled. But this energy becomes kinetic energy as these electrons get motivated to move, and that kinetic energy can be harvested to run mechanical devices. Okay, compressors in the case of an air conditioner, and some of that energy is lost as heat as well. All right, but this air conditioner is in the business of converting 10,000 joules of energy, electrical energy per second, into some other form of energy. And so when you get an electric bill, though, do any of you get electric bills? You're being billed not for power consumption but energy consumption. Okay, so the electric bill bills you for energy. Okay, and do any of you know, I'll tell you this first. When on your electric bill, you're billed for energy consumption, but the units of energy that are reflected on your bill are not joules. They're not the SI units of energy. Does anybody know what the unit of energy is on your electric bill? They're not BTUs, British thermal units. That's another unit of energy that's oftentimes associated with things that heat or cool. It's associated with thermal energy oftentimes. Does anybody know? Kilowatts per hour. Close. Close. William's close. Tyler's got it. Good job, guys. Okay. So it's not kilowatts per hour, it's kilowatt hours. Kilowatt hours. So on your electric bill, you're billed for something that is called kilowatt hour, kWh for short. So let's think about this. All right. So a kilowatt, what is a kilowatt hour? 1 kilowatt hour of energy is 1 kilowatt is 1,000 watts. So it's 1,000 watt hours. What is a watt? A watt is 1,000 joules per second. So a watt hour is joule per second times hour. And what is an hour? An hour is 3,600 seconds. I'm going to run out of space. 1,000 joules per second times 3,600 seconds in 1 hour. So the seconds cancel, and you're left with 3,600 times 1,000 is 3,600,000 joules of energy. So 1 kilowatt hour is a unit of energy. It's because what you're doing is you're taking, so watts, kilowatts, watts is energy per time, and then you're multiplying by another unit, another factor of time. So you have watts per time multiplied by time, joules per energy per unit time multiplied by another unit of time, and there's some unit conversions that go on. But ultimately, if you have energy divided by time multiplied by time, what you're left with is energy. joules. Okay. So you're going from power back to energy by multiplying the hour. Correct. Correct. You're going from, so if you have power, watts, and multiply by time, you're getting energy. You're getting energy. Energy per time multiplied by time leaves you with energy. Okay. So if we look at the homework problem here, let's see. A large household air conditioner may consume 10 kilowatts of power. What is the cost of operating this air conditioner 4.5 hours per day for 10 days if the cost of electricity is 20 cents per kilowatt hour? Okay. So let's go back here. Go back up to here. So we have this, we want to figure out, so the first thing we want to do is we want to figure out how much energy this air conditioner is using, because that's what you're built for. And energy is going to be equal to power multiplied by time. So here we have 10 kilowatt air conditioner, and it runs for 4.5 hours per day for 10 days. So how many hours does it run? If it runs for 4.5 hours per day for 10 days, it's 45 hours. 45 hours total. So 10 kilowatts times 45 hours equals 10 times 40 is 450 kilowatt hours. That's how much energy this air conditioner uses over 10 days. And we could convert that to joules, but in this case, that doesn't get you anything. In fact, it takes you in the wrong direction, because what they want to know then is, well, how much does that energy cost? How much are you billed for that energy? And if it's 20 cents per kilowatt hour, then what you want to know is how much energy you've used in not joules, but kilowatt hours. The units of kilowatt hours. So what should we have? So 450 multiplied by 450 kilowatt hours of electricity multiplied by 0.2 20 cents per kilowatt hour gives you $90. Cost you $90. All right. So I teach a class. Well, Dr. Murphy teaches it too now on energy, and we spend a lot of time thinking about the sources and ultimate uses of energy in our civilization. And when it comes to your domestic life, one thing that you should all know is that in your domestic life, the thing that you use the most energy for in your home is heating and cooling. That's and so in the case of I have a heat pump, so it runs on electricity. That comes up on my energy bill, my electric bill. Other people might have an oil or gas furnace. That those expenses for natural gas or propane or heating fuel, heating oil, that's going to be one of your largest domestic expenses for running your household, energy-wise, your energy consumption. Using a light bulb, think about this way: how much energy does a light bulb use? Well, if it's like a light bulb like this, whoa, it's crazy. That's an LED bulb, and it uses about 13 or 14 watts of power. So how long will that light bulb have to run before it uses 1 kilowatt hour of electricity? And it uses 13 watt hours of electricity per hour. So that's, if it's 13 watts and you multiply by 1 hour, that's 13 watt hours. So it would take 1,000 hours before it uses 13 kilowatt hours of electricity. So that's a pretty long time. Light bulbs aren't really the major energy sinks in your home. You can save energy by converting from incandescent to compact fluorescent to LEDs, and it makes a difference over the long term. But if you want to save energy and consequently money, energy efficiency when it comes to heating and cooling is the place to go. So after heating and cooling the air in your house, anybody want to guess what the next biggest cost is energy-wise in most households? Put it in the comments if you think you know. So number one is heating and cooling your air, okay, in your house. All right, number two, let's see if anybody knows. All right, let's take a look at this other problem here. What is the average power consumption in watts of an appliance that uses 5.3 kilowatt hours of energy per day? Well, if this is energy, so you divide by 5,300 kilowatts of energy, kilowatt hours. Sorry, 5,300 watt hours. That's 5.3 kilowatt hours of energy per day. And then you just divide by the number of hours in a day, and that tells you how much power that thing consumes. Okay, and then you got to do an energy conversion to figure out how much energy is this in joules over a course of a year, and it's a lot. It's 7 billion joules of energy. All right, and one of the things we can learn here is, why do we use kilowatt hours for electric bills instead of joules? Because when it comes to the quantities of energy that we consume, a joule is a very, very tiny amount of energy, and kilowatt hours is a more manageable, convenient unit of energy for the magnitudes of energy that we consume in our households. All right, so let's see. William says washing and drying, perhaps, or heavy-duty appliances. So yeah, I'd say a dryer uses, well, let's say, think about it this way. What do you think uses more energy in a typical month? A hair dryer or a television? What do you think uses more energy in a typical month in a typical American home? A hair dryer or a TV? Let me give you a little context here. So if you look at the power rating on a hair dryer, it's like 2,000 watts, 1,500 watts. It's well over 1,000 watts of power consumed by a hair dryer. A television, maybe 200 watts, 250 watts. So you got hair dryer, let's say 1,500 watts, 1.5 kilowatts. And a television, let's just say 200 watts. Okay, so which of those, obviously there's another factor here, because just based on these numbers, hair dryer has a bigger value. There must be another factor here. In a typical month, which of these appliances uses the most energy? Hair dryer or TV? What would you have to know in order to figure out how much energy is used? These are power ratings. What's the factor you need to know in order to know how much energy is used? What do you say? So power ratings are energy per unit time. So you'd also need to know how many hours each one is used. Right, the time. Right, Chris. Right, William. The time. So I don't know, if you're like my house with 2 kids that are addicted to electronics, the TV's on a couple hours a day. Hair dryer might get used once a week for like 10 minutes. Okay, so how much energy does a hairdryer use if it's on for 10 minutes a week? Not much. How much energy does the TV use if it's on for, let's say, 12 hours a week? A lot more. So, so back to this question, a dryer does use a lot of power. The power rating of a dryer could easily be, 3,000 watts, probably more than that. I'm not even sure. It's probably more. It's probably more like 4,000 watts or 5,000 watts. The dryer uses a lot of power, and it's even got its own dedicated circuit. It's 240 volts instead of 120 volts. It uses a lot of power. But the thing is, dryers, you don't usually, how often do you run it? Maybe 4 hours a week, maybe. So it's not heavily utilized. The thing that I would suspect is the number two most expensive thing in most households is, after heating and cooling your air, heating your water heaters. And the reason is because it takes a lot of energy to raise the temperature of water 1 degree. And we use a lot of hot water. How much energy does a 5-minute shower use? You know what I'm going to do today? I'm going to end with, I made a video a few years ago that I'll try to show it to you. It's my video, so I should be able to do this without breaking any copyright laws. I made it, and it shows the energy in coal equivalent of different everyday tasks, and it's pretty interesting. Okay, so I'll try to show that to you before we end today. Yeah, my dryer's pretty garbage too. I fixed it twice in the last year, and I don't think I'm going to fix it again. I think it might be time just to say goodbye to that dryer. It's like 20 years old. The heating coils keep burning out, and I don't know why. But yeah, it takes like 2 hours to... But you know what? If the heating coils burn out, that's where most of the energy consumption goes. So it's taking longer, but it's not using the same amount of power. Maybe it's not so bad. All right, let's take a look here. Let's go back to the other assignment here now. Number 2 in the second assignment is an integral. You have a force that's a function of x. So it's kind of like Hooke's law, except more complicated. And you want to figure out, well, what's the potential energy associated with work done by that force. So if you take a look at where we derived the formula for elastic potential energy, spring potential energy, you should be able to do that. Of course, it involves an integral of a polynomial, and some of you have never seen integrals of polynomials before, maybe. But if you can do a derivative of a polynomial, you can do an integral of a polynomial too. It's in reverse. So see what you can do with that. We can revisit that later this week if you guys have a lot of questions about it. This is a cool problem because maybe we'll take a look at this problem next time. This is a problem that's, you guys did the Atwood's machine laboratory last week, and you took a look at the Atwood machine laboratory from the perspective of Newton's second law. Well, in this problem it has, well, let's take a look at the problem from the perspective of work and energy. And you can look at it either way. So what do you lose when you look at work and energy? You might lose some information about the direction the masses are traveling, but what you gain is you're just accounting for numbers. Kinetic and potential energy are just numbers. So we do a little bit of work on this right now. We got about 10 minutes. This would be a good problem for the tutorial, for a tutorial too. Well, let's take a look at. Let me take a few notes here, and then we'll switch over to my whiteboard, erasing everything I wrote down about power. All right, so we got the Atwood's machine, and it's got these two masses. I'm drawing a picture. Here, I'll show you while I'm drawing. M1. Oh, I got that backwards. That's M2. There's M1. And M1 is elevated a distance h, and so I don't know why they do this. This is a little bit of busy work. It says M1 is 5.9 kilograms, and it says M2 has 80%, has a mass 80% that of M1. Okay, so you know, when I hear that, I'm thinking, well, why don't we just multiply 5.9 by 0.8, and then we'll write down that means M2 is 4.72 kilograms. 4.72 is 80%. So they're attached to this cord, negligible mass, which passes over a frictionless pulley of negligible mass. So that all that is saying that the energy is contained in the masses of this system. M1 and M2 start from rest after they have each traveled a distance of 2.2 meters. Use energy content to determine the following. Okay, so the initial, so here I have M1 and M2, so I can't really use 1s and 2s to denote moments in time, but what I can say is, let's call that moment A, when the masses start out, and they start out from rest, and then sometime in the future, I want to use a different color. So moment A, moment B, which is sometime in the future, mass 1 is heavier, so the system will have changed, where now mass 2 is higher. These are not drawn to scale, and mass 1 has fallen down, and it's fallen down a distance equal to h. So it started up here, and it's fallen a distance of 2.2 meters. Okay, and so this is where it started. Okay, and it says use energy content to determine the following: the speed of the masses, the magnitude of the tension in the cord. Okay, the speed of the masses and the magnitude of the tension in the cord. Okay, so let's think about energy content. Well, what's the mechanical energy of this system at moment A? It's going to be equal to the kinetic energy at point A plus the potential energy at point A. Okay, well, why don't we, you know, I'm going to redraw this because this is really, well, I'll leave it like that. Okay, and you could say, you know, what is the mechanical energy at moment B? Well, it's going to equal the kinetic energy at moment B plus the potential energy at moment B. And the, you know, so which of these terms is 0? Okay, guaranteed to be 0 based on what we know so far, without making any special assumptions. Which of these terms, here I'll underline them, this, 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 So you have at moment A, kinetic energy and potential energy. Moment B, kinetic energy and potential energy. So which of those terms is guaranteed to be zero based on our knowledge of this problem? What do you say? And while you're doing that, I'm going to look up my coal video. If I can. Which of those what terms underlined in blue is guaranteed to be zero? When did Vimeo become so horrible? Alright, I found it. Anybody? Come on, which of these terms? You have moment A is when the masses start from rest, and moment B is when they've fallen. Well, mass 2 rises 2.2 meters, mass 1 falls 2.2 meters. So which of those terms underlined in blue is guaranteed to be zero in the context of this problem? You guys are unsure of yourselves. So the kinetic terms in this problem are going to be, look like that. 1/2 mv squares. And the potential terms are going to look like this. mgy's. Thank you, Maggie. Thank you. Kinetic, okay. But Maggie's got part of it right. But which one? There's two kinetic terms. There's a kinetic term for moment A, and there's a kinetic term for moment B. So there's Ka and Kb. Which of those is zero? Yay! Thank you, Katie. Thank you, Katie. The kinetic at moment A. So you know that it starts from rest. The masses start from rest. So initially, at moment A, the system has no kinetic energy. Okay? And, all right, so what about potential energy? Well, you got two masses. So there's going to be M1 G Y1A plus M2 G Y2A. So there's going to be two terms that contribute to the system's total potential energy, and that'll be true down here as well. Okay, and ultimately though, when you set up an equality between the total energy at moment A and the total energy at moment 2, what's going to matter is a delta Y, the change in Y, which you know that the change in Y for particle 1 and particle 2 are both 2.2 meters. Or sorry, mass 1 and mass 2 are 2.2 meters. All right, so we'll work more on that on Wednesday. And but between now and Wednesday, definitely work on that problem and see how far you can take it. It's good practice. All right, good practice. Let me see if I can show you this video now. It's only 2 minutes long. All right. Whoops. I wonder if, all right. So can I turn on my desktop audio, and I'm going to mute my mic for a second, all right? And let me know if this works. It'll be nice to know, all right? So in the comments, let me know if you can hear sound when I'm playing the video. All right, here we go. All right. So I made that video a few years ago, and the last one was what I'm doing is I'm actually calculating, taking into account conversion efficiencies from the time you burn the coal to generating electricity, transmit the electricity to your house, and then convert it back into some other end use of electricity. And so those numbers are accurate. So it does take about 2.5 pounds of coal to take a shower, 5-minute shower, or something like that was my assumption. And so why am I doing that? Well, in West Virginia, most of our electricity does come from coal. So even if you have an electric vehicle in West Virginia, if you charge that vehicle from the grid, its CO2 emissions, its effective CO2 emissions, would be higher than a lot of gasoline automobiles. It's something like 30. Its CO2 emissions would be equivalent to a car that gets like 30 miles per gallon in that neighborhood. So it's just interesting, that an electric vehicle is not necessarily does not necessarily have a smaller carbon footprint. It matters a great deal where you get the electricity to charge the vehicle from. And so electric vehicles without renewable energy sources, or I shouldn't say renewable, yes, but when it comes to carbon footprint, what you want is low carbon energy sources. And low carbon energy sources aren't the same as renewable, although there's a significant amount of overlap. Maybe one of you know that there's a major source of energy which would not be considered renewable energy, but has a very small carbon footprint, CO2 emissions. And does anybody know what that is out there? While you're thinking about that, the I lost my train of thought. So in West Virginia, as of like last year, this is changing now pretty quickly. We get most of our electricity, 94% of our electricity on the grid comes from coal power stations, so burning coal. And the transition that's happening very quickly now is from coal to natural gas. Natural gas has about 50% less CO2 emissions than coal per unit energy. So from a carbon perspective, it's a lot better. Of course, natural gas predominantly is coming from hydraulic fracturing, and there's a lot of concerns about the safety of that. So nothing humans do comes with zero environmental impact. It's just the act of living in the world is you're interacting with the world. Nuclear, right? William's got it. Nuclear. So nuclear energy has, and this is data from the United Nations Intergovernmental Panel on Climate Change assessment report, that the carbon footprint of nuclear energy is about the same as the carbon footprint of solar electric electricity. So the promise, you shouldn't discount nuclear. People. The problem with nuclear energy is that it creates nuclear waste, and there's safety concerns about the actual nuclear power plants themselves, and all of that is perfectly valid concerns, and it's based on a history of nuclear accidents and nuclear problems, like at Fukushima power station in Japan when the tsunami hit, 3 Mile Island near where I grew up on the Susquehanna River, and of course Chernobyl in Eastern Europe in the 1980s. And nuclear energy is not renewable. The energy is coming from uranium, which is mined. There's an environmental impact associated with that. And the real promise of nuclear, and I think that this is, it's a topic that splits environmentalists. And the reason is because you have this duality. You have this technology which is very low carbon when it comes to generating electricity, and can, if you look at in the United States, the power stations that produce the most energy in a given year, like 90% of the top 10 power stations when it comes to total energy production are all nuclear power stations. And I think there's one in the top 10 that's natural gas. Okay, but we're getting huge quantities of energy, and one thing that's interesting is there's countries that are shutting down their nuclear power generation, and they're replacing it with things that are more carbon intensive. So their carbon emissions will go up because of this. Yeah, William says they don't go wrong often, but when they do, they go really wrong. So one thing I would say is we as a country shouldn't stop developing nuclear energy, because I think there's real promise in what are called Gen 4 nuclear reactors, Generation 4 nuclear reactors, and it might be 10 years before these things get into commercial operation. But the idea is you can build a nuclear reactor that's inherently safe, in the sense that it can't. The laws of physics will not let that reactor melt down. It will not melt down. It can't. And you can also build nuclear reactors which are called breeder reactors, which actually can take the nuclear waste we've been accumulating for the last 60 years and use it and turn it into new nuclear fuel. So nuclear reactors that actually transmutate nuclear waste into stuff that can be used to make energy, diminishing the amount of nuclear waste. one of the big problems there are that one of the things that you breed in these breeder reactors is plutonium, and plutonium can be used to make nuclear weapons. So proliferation problems, nuclear weapon proliferation problems are a problem. Thorium reactors, yes, thorium seems promising. Reactors, the predominant, I know we're out of time, the predominant nuclear reactor technology used in the United States is pressurized water reactors. And when you have water that's pressurized, you can keep it in a liquid state at much higher pressures and temperatures. The problem is if you get a leak, you lose pressure, and all that water turns to steam like this, and you have explosions. And that's one of the major safety concerns of nuclear power plants. So what can you do? Instead of using water as your coolant and your heat transfer medium, use something else that doesn't have to be pressurized. And liquid sodium is a promising candidate for that, and you diminish the risk of explosion from non-nuclear sources in these power plants. Okay, that's enough for today. So on Wednesday, I'll see you guys tomorrow for our lab session in the afternoon, and on Wednesday we'll take a longer look at this Atwood's machine problem. Okay, but between now and then, work on it. See how far you can take it. All right.